Good day to all of you. I want to begin by introducing myself. My name is David Ash, and I am a mathematician and sometime computer scientist who has been in the field for many years. I want to thank the organizers of this conference for putting it all together and giving me the chance to make this presentation today. So thank you again. So let's get started here. Let me just bring this up. Okay, so I'm here to talk to you today about something called the ASEP, the asymmetric exclusion process. This is a structure that's been studied quite a bit in the combinatorial community for a while now, and there's a number of different definitions of the ASEP that have been explored. The ASEP is, well, we'll talk a little bit further in. Uh, I'm going to be building a lot today on some results of Mortimer and Prellberg. They obtained some power series results that are applicable to a triangular domain. Their work is not necessarily directly connected to ASEP, but Elizalde in 2022 found that projections mapping this work to instances of the ASEP. So we can use that to come up with some power series results for the ASEP, bearing in mind that Elizalde's work was a little bit different, a slightly different focus. So we're going to show how to use Mortimer and Prellberg to find power series results for the ASEP. Now, I should say that there's quite a number of different definitions of the ASEP that are out there. And I'm going to be using one that's in a paper by Cortiel, Mandelstam, and Williams, which is ASEP on a cycle, and rather than on a cycle or a ring, rather than on a straight line, is one that has multiple species of particles, although only one particle can occupy a given space at a time. But I mentioned this just because there's multiple definitions out there. So I won't go too much into the details of the ASEP. The ASEP is a Markov process on the set of permutations of a given partition, and it tells you basically there are certain transitions on this on these essentially balls on this cycle. They can any ball in any given location can move to an adjacent location on either side with a certain probability if that space is empty. And also if we have two if we have two adjacent particles, they can of different species, they can change species. Again, we're talking about the ASEP, which has multiple species here. And so there are different probabilities that are given. This is the definition that I'm using. Other researchers have focused a lot on things like steady state probabilities for the ASEP. That's not going to be the focus today. The focus today is more on power series regarding paths through the ASEP. So don't worry too much about the probabilities here. It's just part of the context. But the focus here is more on the like I said, more on the power series giving paths through the ASEP. We're just using this definition here that others have used. Okay, so what do Mortimer and Prellberg, what do they contribute here? They focus on lattice paths in a triangular domain, which can be a triangle, it can be a tetrahedron, or any simplex of a higher dimension. For the present paper, which is this kind of more preliminary work, we're going to be focusing just on the linear version. So you basically just have a lattice of a straight line that Mortimer and Prellberg are using, and you can move back and forth from any point to any other point. But if you get to the end point, you obviously can only move back, and so that's kind of the simplest example they focus on. They also go after triangles and so forth. We won't get to that in this talk today. They do, however, have a generating function which counts n-step walks starting at UV. So UV would be, it could be 6, 0, it could be 0, 6, or anything in between in there. And this is the generating function. It's a little bit messy, but it is a definite generating function that tells us the number of paths that start at UV and that kind of end at a particular end at any point in the lattice. Now, this has a certain relationship to fixed paths. Here, the value p is actually itself a power series in the variable t, and it's given by this particular generating function. And in this case, this generating function is very close to the generating function for fixed paths, which is also the generating function for Catalan numbers. The only difference is that for that we would have to replace 2t with 2t squared. So otherwise, it's the same thing. Okay, so the inequality about bijection. It is a bijection between that happens between various combinatorial structures. They can be paths and simplexes, which is what Mortimer and Prellberg are interested in. It can be the standard cylindrical flow, or it can be the ASEP represented either as a graph or as a micrograph or as a multigraph. I won't get into the details of that difference, but we are going to be mainly interested today in the bijection between paths and simplexes and the ASEP. Note again, that for this bijection, it's a one-type ASEP. So there's basically balls of only one species in the bijection that's going to be explored. That there's all these exploring in there. We're going to get a little bit beyond that today. We're going to be able to expand that from one type to two type by essentially expanding a little bit more. Okay, so how can we generalize the work of Mortimer and Prellberg? Well, we want to first find a generating function starting and ending at one particular point, of 0. And their generating function starts at one point, but it can end anywhere. So it's we need a little bit more than that. But we can use their results to get it. This is just essentially a building block we're going to need to eventually get to what we really want to do with the ASEP. So we denote this, we're going to introduce some new notation here. We're going to denote this by GM0M0. That represents as starting and ending in an M0. And that's kind of building on the previous notation where GM0 is representing paths starting in M0 and stopping anywhere. So I've told you what that is. Now, how do we, what can we say about this? Well, right now, to evaluate GM0, M0, we're going to actually start by coming up with a different combinatorial representation for the original path, which we already know the generating function for. And that's the GM01. So we're going to assume that we start and end. We start in M0 and that we're going to return there exactly k times in the path. And this can be represented by this power series. And note that we don't we're using n-1 and n-1 there. The reason for that is if you kind of go back to the original lattice here. If we visit an endpoint, then immediately after visiting that endpoint, we have to go to the point adjacent. And if we're talking about what happens before we go back to the endpoint the next time, we're limited to n-1 spaces rather than m. So that's how come we get the n-1 in this. So that tells us when we end at M0 and we return there exactly k times, we get this. We actually get n-1, but we get it. We raise it to the power k because we're potentially going to get up to k times. So the other case is that the path ends elsewhere than m comma 0, and this is to actually evaluate the original the original generating function. So in this case, the last part of the path is going to be represented again by this G-1 dot. And so this gives us this overall generating function, which is just a different representation of the generating function that more and more already provided. But it has the big advantage that it kind of enclosed in there is the generating function that we're interested in. So we can sum the infinite series, and then solving it, we end up with a generating function that we want, which again, just a building block, what we really want to build up to. Now, what happens if we have paths starting and ending at different endpoints? So in this case, we want to find the generating function starting at m0 and ending at 0m, which will be denoted by gm00m in similar notation. Okay, so again, we're going to work from gm0 x comma t, and we're going to find a series of segments. First segment goes from m0 to 0m, the second segment 0m to m0, and so on. The last piece of it is going to be a little bit different, though, based on whether we have an even or odd number of segments, giving us a functional equation, which differs depending on whether we have an even or odd number of segments. I'm not going to work through all the details here, but that's what we come up with. But we do, when we sum it up, we come up with this thing here. We arrange terms. We get this, which is actually a quadratic equation in the generating function we want to come up with, which we can solve to come up with the value that we want. Okay, so all of this so far is just with the one type ASEP. We now want to talk about the main ASEP result, which is going to be a two-type ASEP. So again, we just worked with the one-type ASEP. For the two-type ASEP, the behavior is going to be similar except with the endpoints. So if you, again, let's go back to the original diagram here. Yeah. So in the bijection that ICECA is proposing, we, essentially the endpoints represent points where the two particles, we have two particles of different species. The endpoints represent the points where the two particles are adjacent. And when they're adjacent, we can do different things. We can the two particles can then switch places, which is a little bit of a different thing that can happen. But when the two particles are, as long as the two particles are not adjacent, the behavior of this is pretty much the same as it is in the one type ASEP. So kind of going back here. Yeah, so the behavior is similar except the endpoints. The endpoints, however, the particles may end up switching places. And we're going to mark a switch in one direction by d in the generating function, and in the other direction by 1 over d. So if you had, for example, d to the n, that would mean that the two particles have switched places in one direction, d more times than they've switched places in the other direction. So anyway, we're going to let lambda be this permutation with 2, 1, and an arbitrary number of zeros. And the ASEP power series can then be computed. I'm not walking through all the details here in the interest of time, but I think you can see that it's going to be similar, except you have to do something special when you get to the endpoints to incorporate the fact that the particles can switch places. And you do end up with this this generating function, which gives you a power series for for the ASEP, which I believe is a new result. But there's definitely opens the door to further research in a number of different areas. First, it should be integrated more fully into Elizalde's work. I believe there will be more of an embedding of the ASEP into it won't be a bijection, it won't be a one-to-one map, but it'll be a many-to-one map. But embedding that in where essentially Elizalde kind of tells us what happens whenever particles are not changing places, whenever it's just particles moving around. And so we can integrate that, but we then need to expand that mathematical structure to deal with the case where it's not, particles are switching places. So again, lead to embeddings and not projections. Also, obtaining more general results. Mortimer and Prellberg do provide more results than focused on so far in this talk. They do talk about triangular domains rather than just domains on the line. The results are not as complete for triangular results. So how much of that we're going to be able to incorporate, I'm not sure, but that needs to be explored. It hasn't been fully explored as yet. So again, let's look at that further. There's also something called the ASEP, the doubly asymmetric exclusion process results. It's a work that I've introduced in the past, and other researchers have taken it up a little bit. I do have some results, but I'm not presenting today as to how this affects DASEP and getting stuff in there, and we'll be interested to incorporate that with the work of others in the DASEP space. So thank you for your time. Please post questions to the video or email me. That's my email address there, and then also. The extended abstract is available on arXiv, and that is a QR code for the extended abstract. Thank you once again, and have a great day.